Edwin Hubble, the famous American astronomer, whom the telescope Hubble was named after, was born in 1889 and died in 1953. He had a remarkable role in how we understand the whole universe now, its history, how it developed, and its unbelievably vast extents. He discovered that the universe goes beyond the Milky Way, which was not known before until the 1920s. It was the first time in history that we, human beings, knew something existed beyond this Milky Way, the galaxy where our solar system is located in the middle of one of its spiral arms. He was the first person to establish the distance to other galaxies. He calculated the distance to Andromeda galaxy, which is 2.2 million light years, and confirmed that Andromeda is not part of the Milky Way. It's a separate galaxy. He discovered that the velocity of distant galaxies increases with distance from Earth. He also developed a classification scheme for galaxies. In this episode, we are going to go deeper into his discovery about the velocity of distant galaxies increasing proportional to their distance from Earth. At the beginning, we need to remind ourselves about the Doppler effect. When a wave source moves away from the observer, the transmitted waves get elongated due to the increase of distance traveled. For light waves, this elongation means a gradual change of color from violet side towards the red. This is referred to as the redshift. The more the shift towards the red color, the faster the object is traveling away from the observer. When Edwin Hubble analyzed the light spectrum coming from the stars in distant galaxies, he received it always with a redshift compared to the reference laboratory spectrum. The farther the galaxy was, the more redshift it gave. These results confirmed the expansion of the universe, similar to a cake stuffed with raisins, growing in size while being cooked in the oven. To accurately calculate the expansion rate of the universe, astronomers used 3 steps to measure it to an unprecedented accuracy, reducing the total uncertainty of the measurements to only 2.3%. Beginning at left, astronomers used the Hubble Space Telescope to measure the distances to a class of pulsating stars called Cepheid variables, employing a basic tool of geometry called parallax. Parallax is the apparent shift to an object's position due to a change in an observer's point of view. Knowing the distance between the two observing points, which is the Earth orbit diameter, and the change in star angle, the distance to the star can be derived. The 2 black boxes at the left side show how astronomers used Hubble to measure the parallax to Cepheid variables. They had to gauge the apparent tiny wobble of the Cepheids due to Earth's motion around the Sun. The wobbles are roughly the apparent size of a grain of sand seen 160 kilometers away. Once astronomers calibrate the Cepheids' true brightness, they can use them as cosmic yardsticks to measure distances to galaxies much farther away than they can with the parallax technique. The rate at which Cepheids pulsate provides an additional fine-tuning to the true brightness, with slower pulses of more luminous Cepheids. The astronomers compare the calibrated luminosity values with the star's apparent brightness as seen from Earth to determine accurate distances. Once the Cepheids are calibrated, astronomers move beyond our Milky Way to nearby galaxies, shown at center up to 100 million light-year. They look for Cepheid stars in galaxies that recently hosted another reliable yardstick, type LA supernova. Exploding stars that flare with the same amount of brightness. The astronomers use the Cepheids to measure the luminosity of supernovae in each host galaxy. They then look for supernovae in galaxies located even farther away from Earth, beyond 100 million light-year. Unlike Cepheids, type LA supernovae are brilliant enough to be seen from relatively longer distances. The astronomers compare the luminosity and apparent brightness of distant supernovae to measure the distance where the expansion of the universe can be seen. They compare those distance measurements with how the light from the supernovae is stretched to longer wavelengths by the expansion of space. They use these two values to calculate how fast the universe is expanding now, a number called the Hubble constant. It equals 67.36 km per second per megaparsec. 1 megaparsec equals 3.26 million light-year, or simply 20.66 km per second for each 1 million light-year. This means that for every 1 million light-year, the universe expansion speed increases by 20.66 km per second. Knowing this, the location where the universe started its expansion in what is known as the Big Bang can be located. A galaxy which is nearer to the center will have less expanding speed from Earth than a galaxy which is farther away. Measuring the expansion speed in all directions of space can show a variation that can be used to determine the location of the Big Bang. To our surprise, the universe expansion speed was found to be the same in all directions at each equal distance from Earth. This result meant only one thing. Our planet Earth is located very much at the location where the Big Bang started. We don't mean here that everything is rotating around Earth. Due to the present accuracy of the expansion speed measurements, around 2.3%, and the vast size of the universe, the solar system, or maybe the whole Milky Way galaxy, represent the center. With the further advance in our measuring technologies, we can achieve more accurate results in this regard. This episode just explained how we discovered, surprisingly, that we are living very much in the center of the universe by evidence taken from solid measurements. But for many, Earth is not located at the center of the universe. To support this claim, two ideas were introduced. Keen to know more about them? This will be our subject in part 2 of this episode. Thanks for watching and see you in part 2.